All right, so now let's look at an example to illustrate before we go into more details. Consider for this example a 1D conservation law, which we've written there in conservative form, and suppose that we divide the one domain, a 1D domain, we divide it into cells, and it's going to have, so let's write first our mesh points. We have I minus 1, I minus 2, I plus 1, I plus 2, and so on. But we look at cells which are actually, this is a cell where we have from here to here, this is our delta x. So we associate a finite cell to each mesh point. In this 1D example. And we have, for example, here cell I has two cell faces. At the midpoints, I minus 1/2 and I plus 1/2. So with the central difference scheme, we could write the equation without worrying about the time discretization yet. We could write dui, that's I, sorry, dt, plus, we're using a central difference, so we're going to look at f at the midpoint, I plus 1/2, I plus 1/2, minus f at I minus 1/2, and the spacing there between these two is delta x, equal to qi. That would be a central difference using the midpoints. Now we could do similarly at the points I plus 1 and I minus 1. And we could get du I plus 1 dt plus, so let's imagine now the I plus 1 has a cell over here that goes to the midpoint here. This midpoint here between these two is I plus 3/2. So that would be f I plus 3/2 minus the point on the other side here is again this one, which is f I plus 1/2. So this would be our central difference for the point I plus 1. Now for the point at I minus 1, this point here, we will be looking at this central difference here, so it's f at I minus 1/2 and f at I minus 3/2, where by f I minus 3/2 I mean this point here. So we're using these other midpoints here to extend our central difference formulas to these 3 points. So now, suppose that I add these 3 equations and divide by 3. Add these 3 and then divide by 3. And what I'm going to get is a consistent discretization of the conservation law for a cell. Let's call a cell here this call this point A and this point B, and so I could have for this big cell that covers 3 delta x, if I add these 3 and divide, so if I add these 3 equations and divide by 3, I'm going to have a consistent discretization for that big cell. Cell AB that goes between I minus 3/2 up to I plus 3/2. So ddt, you can, I'm going to add all the terms here that are time derivatives, and I have ui plus 1 plus ui minus 1, all on the left hand side, and divided by 3. I divided this by 3. Then I'm going to add up these 3 flux terms. When I add these 3 flux terms, what's going to happen is that you can see here the term I plus 1/2 is going to cancel out here, and the term I minus 1/2 is also going to cancel out, and I'm only going to be left with I plus 3/2 and I minus 3/2, which is consistent with the central difference discretization on the whole cell AB. Nothing strange there. It looks like it should. Divided by 3 delta x, of course, and on the right hand side we have the sum of the 3 source terms divided by 3. So this is consistent with if we had with what we would have obtained if we had discretized directly So if we had written directly a scheme applied directly to cell AB would have given us DUI. So that's the center, dt, the center is of cell AB, plus fi plus 3/2 minus fi minus 3/2 divided by 3 delta x and qi. So you can see that the flux balance is identical, and the only difference is that in the top one, we have an average of the 3 mesh points. Okay? Now the interesting thing happens when we compare this with what would happen if we were to.
Right. So you have QI as your source term, but in the second.
So if I am just standing here as the center of this whole cell, I would have only used the source term in the center of that cell, everything, all of the variables calculated in the center of that cell, and would have looked at the fluxes across the walls of that cell, across the surfaces. In this case, it's just a 1D example, so the fluxes appear in the point A and the point B. and all of my flow quantities are evaluated at the center of that cell. The one above, the only difference is that I have my source terms and my flow variables actually are averaged on 3 points inside the cell. The way I obtain the top one is by considering this smaller, finer grid and adding up. But all of the internal surfaces here canceled out, like I showed in the previous sketch, where we had a quadrilateral and 3 volumes inside. All of the internal surfaces canceled out, and you see here the effect of that, resulting in the identical flux term, whether I consider a bigger volume or a set of smaller volumes within it. It's analogous to the sketch we did before. Now, the interesting thing is when you use, for the same exercise, the non-conservative form of the equation. So let's see what happens there. So for this non-conservative form where A of u is our Jacobian, so A is equal to df du. It's a 1D example. For example, in the Burger's equation, we had A is equal to u with f equal to u squared half. So now we're writing a general case here. And so let's apply a center difference at the point I, and we would get dui dt plus A at point I, and here we're going to use the central difference, second order central difference with the midpoints, so ui plus 1/2 minus ui minus 1/2 over delta x equal to qi. So this is our, where we're using the abbreviation AI is the Jacobian A evaluated at ui. So now we're going to apply it to the points I plus 1 and I minus 1, similarly to what we just did, and we would have dui plus 1 dt plus A I plus 1, and we have here just the same as we had before. The midpoints are for this guy ui plus 3/2 and ui plus 1/2. And now for ui minus 1, we have the Jacobian at I minus 1, and the midpoints in this case are ui minus 1/2 and ui minus 3/2. So now, just like we did before, add these 3 together and divide by 3 to get a discretization of the bigger cell that went from A to B in the sketch that I just had. We are still considering the same mesh in 1D. And what do we get? We get ddt ui plus ui plus 1 plus ui minus 1 divided by 3. And we're going to have, actually now the fluxes are not going to cancel out because I have this A over here. So we get AI, I have to write them all out, ui plus 1/2 minus ui minus 1/2 divided by, I've divided by 3, so let me just write 3 delta x. I've divided all of this equation by 3. AI plus 1 ui plus 3/2 minus ui, what was it? Is that correct? Yes, plus 1/2 and divided by 3 delta x. And I have another term which is ai minus 1 ui minus 1/2 minus ui minus 3/2 divided by 3 delta x. And all of that is equal to this average of the 3 fluxes. So qi plus qi plus 1 plus qi minus 1 divided by 3. We can rewrite this so that we can kind of reconstruct what we would want to have for the cell AB. For the cell AB, we would want to have, for the flux term, we would like to have AI multiplied by ui plus 3/2 and minus ui minus 3/2. We want the edges of the big cell AB, right? So let's put that in, basically add and subtract from both sides of the equation, and we would get this doesn't change. The three values of u averaged out, and I want to have AI multiplied by ui plus 3/2 minus ui minus 3/2. So I have to basically subtract this from the other side of the equation. I'm going to move everything to the other side. I'm going to write qi plus 1 plus qi minus 1 divided by 3. And we still have minus some terms, which I'm going to write down here. And they are ai plus 1 minus ai multiplied by ui plus 3/2 minus ui plus 1/2 divided by 3 delta x. You can work this out. AI I did earlier today, and it works. AI minus 1. And we have ui minus 1/2 minus ui minus 3/2. So we have all these extra terms, right? I'm going to make a reference to that. Now, if we had applied a direct discretization on the cell AB, we would have only the terms in the first row. So only these terms would appear. Only these terms would appear on a direct discretization on cell AB. So we have additional terms here. These extra terms result from the fact that the flux contributions don't cancel out internally when I'm using the non-conservative form of the equation. Okay, that's the important message that I wanted to drive home here. Let's summarize a couple of things here, and now this prepares the ground for discussing the finite volume method. Now we understand why it is important to have the conservative form. So they were both different, we noticed. The results were both different when we used the conservative and non-conservative form, and the extra terms on the right-hand side of the equation that I put a little asterisk on result from the fact that the flux contributions at the internal points of the cell AB do not cancel. And so they appear as additional source terms. Basically, we're saying that the discretization of the non-conservative form of the equation leads to source terms. Internal sources, these numerical internal sources. Now it happens that this is a kind of like an additional error, okay? And an important note here is that the conservative and the non-conservative form of the equations are, of course, mathematically equivalent, right? But numerically, they're not. When we use them to develop a numerical scheme, they're not the same, okay? This is very important to really understand and remember. Mathematically, they are the same. And this is for arbitrary nonlinear fluxes. It doesn't matter what the form is. Arbitrary nonlinear fluxes. But their numerical implementation is not. It's not equivalent, right? Now, if we look at those extra source terms, we can do a Taylor expansion and see that the extra source terms can be considered like a second order discretization proportional to delta x squared multiplying AX, subscript X represents derivative, AX multiplied by UX, and all of this again, derivative with respect to X. Now, these are, of course, of the same order of the truncation error, so they're negligible, but they're negligible as long as these derivatives are small. So for smooth flows, continuous functions, then these terms are negligible. They're same order as the truncation. But in fact, through experience over time, numerical experiments have consistently showed that the non-conservative formulations are generally less accurate than conservative ones, and this especially applies when there are discontinuities, when there are shocks in our flow. So for discontinuous flows, for example, shocks, these numerical source terms can become important.